Let's do an example of unit tangent vector and principal unit normal vector. So let's say you're given the trajectory curve in degree b, which is 2t and then 4/3 and then like this. And the first question is find the unit tangent vector. And the second question is find the principal unit normal vector at some given point 4. When t is 4, find the principal unit normal vector. Now let's recall what unit tangent vector means. First, if you differentiate this, what do you get? The derivative, well, if you think about this as a moving trajectory, moving particle's trajectory, then this is like the position of the particle. If you differentiate the position, you get
Velocity.
velocity. Okay. And we know that velocities are tangential to the trajectory, right? So this is a tangent vector. However, is this a unit vector? What does unit vector mean? Magnitude of 1, right? So can we be sure that this is a unit vector? Normally not, because the magnitude of this is called the speed, and speed is whatever this particle is moving at, right? If it's going fast, this value will be big, the magnitude of this will be big. If it's moving slow, then the magnitude of this will be small. Okay, so we don't know. And therefore, in order to make a unit tangent vector out of it, the word in here is unit, what do? When you have a vector that's not a unit vector and you want to make a unit vector out of it, what do? You divide by its norm. Now, such a process is called normalizing. Okay? You say, taking a vector and dividing it by its size is called normalizing. We normalize the tangent vector to get the unit tangent vector. All right, so let's try to calculate this. This simply means you have to differentiate. So if you differentiate 2t, you get 2. Differentiating this, 3/2 comes down in front. And you have to subtract 1 off of 3/2. What's 3/2 minus 1? 1/2. And then 2 comes down, so it's 1/2 times 2t. That's what you get. And you can see that these can be canceled. Some of these cancel. 3 and 3 cancels here. 2 and 2 cancels. And 4 and 2 can be reduced to just 2. 4/2 is just 2, right? So that's what you get if you simplify. But that's not all. You have to divide it by its norm. How do you calculate the norm of a vector? Square root of square each one of them, right? So you have 2 squared plus 2 times t 1/2 power squared plus t squared. Let's calculate this further. So you have 2 times, I guess, square root of t, right? 1/2 power is square root, and then t. That's what you have on the top. On the bottom, you have square root of 4 plus 2 squared is 4. And what's square of t to the 1/2 power? It's just t, right? And then t squared is t squared. So you get that. Now you can leave it like this if this is all you have to calculate. But because you have to use this to get the next answer, you should simplify as much as possible if you can, okay? So let's think about how you can simplify this. How can you simplify the denominator? Huh? You have to factor. One common mistake that I find students doing is they would take the square roots of each individual ones. No, that's you don't do that. You're in calculus 3. Don't make that silly mistake. Okay? Yeah. If you have addition, you can't do that. Okay? The only thing you can do is think about this as x squared plus 4x plus 4, right? And try to factor it. It's so it will be t plus 2 times t plus 2. Can you see it? Okay. So if you factor it like that, then you get 2 square root of t comma t square root of t plus 2 squared, and the square can cancel with the square root, leaving you with somewhat better manageable form, which is t plus 2. All right. Okay, now let's go for, so that's the answer to A. That's the unit tangent vector. Now let's go for B. What's a unit, principal unit normal vector? Well, because tangent vectors don't change its size, so if you have a trajectory and you have the tangent vector at each point, what it does is as tangent vectors follows the curve, it only turns. It doesn't change its size. So when it's only turning, think about the direction of the change. The direction of the change will be perpendicular to this vector that you have, because if it's only turning, the derivative is tangential to this turning, but this turning is just circle. It's a circle because this radius doesn't change. Right? If the radius doesn't change, then the derivative will be tangent, which means it will be perpendicular. Okay? And that's why we take the derivative of the t hat. We take the derivative because I know that this is perpendicular to our t. Okay? Because this is tangential to the curve, this thing that's perpendicular to t would be also perpendicular to the curve, and that's where this word normal comes from. What does normal mean again? Perpendicular. Right? Orthogonal, normal, perpendicular, 90 degrees, right angles. They all mean the same thing, 90 degrees. Okay? So this is normal to the curve, but the reason that you put this word principal is because there are many directions that's normal to the curve. So see, not only is this direction, which is the direction of n, is perpendicular to this curve, but this is in 3D, so you could have something like that or that's perpendicular to the curve. So there are infinitely many directions which is perpendicular to the curve, and among those we are thinking of one principal direction. Now I will later explain in the next question that why this principle is meaningful. Okay? When you have the acceleration involved, it will become meaningful. Okay? All right. So that we know that that's the principal normal direction, but is it a unit vector? We can't guarantee that, right? So what do? Normalize. We divide it by its size. See, if you keep making sense out of these formulas, then you don't have to memorize much. And that's how you can do well in Calc 3. You don't want to be memorizing everything. You want to see if you can understand the formula as much as you can. Of course, it's not always possible, but if you can understand it, try to understand it, and that way you will have less to memorize. All right, so that's the formula. That means I have to differentiate this, because that's your t hat, right? That's your t hat. We have to differentiate this. Now, when you try to differentiate this, you're basically doing 3 quotient rule, because if you think about it, this is really 2 divided by t over t plus 2, 2 radical t divided by t plus 2, and t divided by t plus 2. That's what it is, right? So you have to apply quotient rule here, here, and there. Okay? That's a lot of work. You don't want to be doing that, right? So instead of trying to apply quotient rule 3 different times, here's a slight shortcut. The shortcut is that here's the quotient rule. F over g prime is equal to f prime g minus fg prime over g squared. That's the quotient rule, right? Now the shortcut is that even though this is primarily for functions of a single variable whose output is a scalar, you can actually take f to be this entire vector. So this is true even if the numerator is a vector valued function. Now there's no division for vectors, so g has to be a scalar. You can't divide by a vector. You can only divide by a scalar. So g has to be a scalar, but f could be a vector valued function, and this still works. And that helps us because then it saves us from having to do 3 different quotient rules. Okay? So let's try to calculate it. T hat prime t is, first you have to differentiate the top, that's your f. If you differentiate that 0, do you know the derivative of square root of t?
1 over square root of t.
Yeah, you should memorize that. 1 over 2 times square root of t. Okay? This appears frequently enough that you should try to memorize this one. Okay? And these are the things that you do have to memorize. Okay? There's some things you can just get by understanding it, and there's no need to memorize. These are something that's what you need to memorize to make your calculations simple. Okay? All right, and then if you differentiate t, you get 1 times the denominator. What's the denominator? T plus 2. Right, that's the denominator. Minus, the formula here says you have to now keep the f unchanged, so that just gets copied over here. 2 radical t, and then multiplied by the derivative of the denominator. What's the derivative of t plus 2? 1. And divide the entire thing by t plus 2 squared. Okay. And then let's continue. 2 cancels. Let's see. 0 minus 2 is negative 2. Oh, no, that's not right. Oh, that's still right. Okay. Now, and then if I multiply t plus 2 to 1 over radical t, that's t plus 2 over radical t. And then this one is 2 radical t, so that I have to subtract. And then 1 times this is t plus 2, and then you have to subtract by t. And then you have to do that. And I guess t and t cancels. So that's what we get for t prime of t. But this is not all. You still have to normalize, right? And that's still a lot of work. So let me try to help you out a little bit. First, notice that we're not really trying to get n of t in general. We're trying to get n of 4, right? So instead of having to normalize this entire thing, which would end up in horrible, very gigantic square root of square, 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 rather than that, the idea is first try to find n of 4. Just write down what I would get if I put 4 here. So by n of 4, I mean I need t prime at 4, and then I have to divide it by its size. You just have to normalize this after you plug it, right? So let's do that. T of 4 is, let's see, negative 2. Square root of 4 is? 2. Square root, not square root. And then 4 plus 2, that's 6. And the square root of 4 is 2. And then 4 plus 2 is 6. 6 squared is 36. So that gives us, let's see, negative 2, 3 minus 2, then 3 minus 4, that's negative 1, and 2. And then you have 36 in the denominator, okay? So that's t of 4, and now you have to normalize this thing. Now, you could write this as negative 2 over 36, negative 1 over 36, 2 over 36, and then take the norm and divide. But let me show you another shortcut. If you have a vector and another vector which is like over 36, if you normalize this and normalize this, would they be different? I claim that they should be same. If you have the same vector but with different size and you normalize them, would you get something different? You would be getting the same thing because normalizing means you change the length to 1, right? So it really doesn't care what length it was before. Right? So normalizing this would be dividing by its size, whereas normalizing this would be doing this. Right? But then 36, well, then if you think about it, this is, you're taking a vector and dividing it by 36, so you shrink it down and then you're taking the norm. That's same as taking the norm of it and dividing it by 36. Is that right? Yeah. And then you multiply 36 top and bottom, and you get the same thing as before. Right? So in here, why am I saying that? So in here, how can that principle be applied? Rather than normalizing this whole thing,
normalize the top.
just normalize the top. Okay, so that's the shortcut. Okay, so the tip is if you have some positive number multiplied or divided to a vector, the negatives you have to put it inside because it has to do with 180 degrees difference in direction. But as long as you have something positive dividing, or it could be something multiplied, those could be completely ignored when you're normalizing. That's the second tip. All right, so let's continue. Therefore, what we know is that n of 4 is the normalization of negative 2, negative 1, 2, which means you have to divide by its size, so it's negative 2 squared, negative 1 squared, 2 squared, which is negative 2, negative 1, 2 over square root of 9, right? Because 4 plus 1 plus 4, that's 9. And square root of 9 is 3, so you have negative 2, negative 1, 2 over 3. Okay? So that's your normal vector at 4.